Hello, my name's Fleur Loveridge. I'm an Associate Professor of Geostructures in the School of Civil Engineering at the University of Leeds, and it's my pleasure to be here with you, at least virtually, for this iYGEC in Sydney. I'm tasked today with telling you a little bit about what I think some of the past and future challenges might be in geotechnical engineering. And I'm going to do that by reference to a bit of my own personal journey, how my own career develops, and perhaps how we can use that as a mirror to look at some of the changes that have been happening in our industry and our world. Here in the photograph on the right, you can see a very young me as an earth science student looking at cliffs in the south of England. I've come a long way from then, and the things I'm going to mention on the way are how things all began for me in the construction industry building things, how I soon actually moved to work on more sustainable initiatives before taking in energy, climate change, and some thoughts about the future. So let's begin with a bit of construction, but actually not just construction. I'm going to talk about iYGEC and how I ended up going from Kent to Bulgaria. So my first engagement with the ISSMGE came over 20 years ago. I won a paper competition organised by the British Geotechnical Association, of which one of the prizes was the attendance at iYGEC, which then in 2001 was held in Bulgaria near Plovdiv. Unfortunately, I couldn't find any digital photographs of me at Plovdiv, so I'm having to share this image of the beautiful city instead. It was the autumn of 2001 when I went to Plovdiv for iYGEC. It was not long after September the 11th. And the world was already starting to change. Maybe we didn't know it quite so much then. I had an absolutely amazing time at iYGEC, and I hope you're all doing so at iYGEC at the moment. I met lots of interesting people, had lots of interesting discussions, and still work with the fellow delegate from the UK who I went to Bulgaria with at that time. I was at iYGEC presenting a paper. The paper was about propping of deep excavations from what we then called Channel Tunnel Rail Link, but went on to be called High Speed 1, the construction of the first high-speed railways in the UK. I was on secondment to Skanska Construction, and part of my role was to calculate the prop forces in excavations such as these shown here, and work with the observational method and monitoring of the prop loads and wall deflections to check everything was happening as we expected. I'll just share here a few results from that paper. We've got a graph of prop loads against a number of different design cases. You can see in blue the measured prop loads, in orange the original design, and in kind of grey colour an alternative method of calculating the prop loads using an empirical method called the distributed prop load method, or DPL. What we observed during the construction of the scheme was that most of the design calculations were significantly larger than the measured prop loads. They came closer together in the cases on the left-hand side of this chart where we used the observational method. So we used less conservative parameters in the design and measured and monitored what happened since. But on the right-hand side where we weren't doing that, you can see that the design loads are very much higher than the construction, and that the distributed prop load calculated loads are somewhere in between. By conducting this review, we were able to justify the use of the distributed prop load on upcoming schemes, not only saving time in terms of design effort, but also saving time in terms of construction and cost in terms of the size of the props that we could use. Now, at this time in my career, I have to say, I wasn't really thinking about the big issues of the world. I was just getting on with the excitement of designing things that were getting built and seeing civil engineering structures come to life in front of my eyes. It was a very formative time. After I finished on site, I went back to the office and I worked for Mott MacDonald in their office in Croydon, just south of London. And sustainability became something of a theme. At that time, we were mainly defining sustainability in terms of the Brundtland definition, the balance of economic, environmental and social factors. I was asked to lead an initiative called Managing Sustainable Companies, or MASC. It was an initiative that was developed by the Building Research Establishment and the Construction Industry Training Board in the UK. The basis of the idea was that sustainable companies would make more efficient use of resources, prevent harmful and potentially irreversible effects on the environment developing as a result of their business, and respond to people's needs. And that's not just people in the community, but also the employees of the company and all the supply chain employees that we engaged with. Effectively, it was a business improvement initiative, and we looked at how we were doing against a number of important indicators and developed plans to how we can improve. The aim being to develop a company that developed and demonstrated corporate social responsibility and delivered financial benefit, as well as improved corporate image, and maintained a competitive advantage through these kinds of innovations. It was great to be working in a culture where these kinds of things were our aims. And I think you can see that in a couple of the projects I'm going to present in a moment. Around this time, I was fortunate enough to be working on the design of the new Wembley Stadium in London. This is one of the iconic football stadiums in the world, and as part of the construction, there were land level changes on the small site. 30,000 cubic metres of backfill were required to large retaining walls, but there were no local sources of high quality granular fill, I should say, and we saw congestion on the roads around the area and the pollution that resulted from that. So it was obvious from an economic point of view that we should be trying to reuse the London clay fill that was already available on the site. And this was quite an unusual thing to be doing behind both large gravity and anchored walls, and required a lot of sophisticated design analysis by my colleagues. Also at that time, we undertook an assessment to see what the benefit was in other respects. So we knew it was going to be cheaper, and we showed that the cost benefit ratio was about 6.5 to 1 for using these local site one materials, even though they were less high quality in geotechnical terms. But we also managed to show that we were embodied energy savings in a ratio of 60 to 1, and CO2 emissions equivalent savings in a ratio of 124 to 1. As well as improve local impact by avoiding 18,000 lorry movements to bring additional fill to site. Around this time, I also started working on my first projects related to the stability of embankments and cuttings, and this has been a theme in my career ever since. We started looking at how vegetation could be used as a sustainable tool. We were working for London Underground and Network Rail at the time. And I'm showing here some data from monitoring of a clay railway embankment in London. You can see two lines, a line here that doesn't move very much, which represents an embankment that was covered with grass, and a line here which moves significantly, which represents an embankment covered by trees. These two embankments showed significantly different degrees of seasonal movement depending on the vegetation cover. The embankment that was covered with trees had the benefit of reduced pore water pressures due to the water extracted by the tree roots, but it also suffered these damaging deformations up to around 45 millimetres as the embankment settled. This was due to the shrink swell in the clay embankments. Hence, there was a bit of a catch-22 and a trade-off between the positive and negative benefits of using vegetation. We also needed to think about other potential benefits of vegetation, providing habitats and green corridors within cities, as well as visual and acoustic screening. It was the start of beginning to think about geotechnical engineering in a different way. I also started to get involved with work on the energy challenge. In 2001, Heinz Brandl gave his Rankin lecture on energy piles and other thermoactive ground structures. And I've taken an image from his geotechnique paper here to illustrate a building heated by a ground source heat pump that could be sourced either from shallow ground heat exchangers or from piles, energy piles, where foundations are used to ground heat exchangers. We did some initial consultancy on this at Mott MacDonald, but then I took a leap of faith and decided to go and study for a PhD in energy piles. The hypothesis was that there was a lack of design approaches for the energy that could be obtained from using energy piles or other energy foundations, and that this was as important as looking at the classic geotechnical problem of whether we were concerned about additional stresses and strains or settlements from these structures. I'm just here going to mention a few highlights from my PhD and early postdoctoral work. I published some of the first analytical relationships between the temperature change with time for a given heat input or output for energy piles, which is shown on the top here, where we have non-dimensionalized temperature change against time, a number of different curves for different configurations and geometries of energy piles. I also did some work looking at the factors that quantified that influence on energy efficiency. This was based on numerical simulation and showed the importance of making sure we put enough heat transfer pipes within the piles to really draw the benefit from the greater heat capacity inside large foundations. Since that time, I've continued to work on energy piles, but not just energy piles, energy from all sorts of buried infrastructure. This picture here shows me on the construction site of Melbourne Metro a few years ago with Australian colleague Roman Azilio from the University of Melbourne, where we were discussing the potential to get heat from the metro and other infrastructure around the world. Recently, I've been involved in an assessment of the potential to get heat from buried infrastructure in the UK. In the UK, we have about 28 million homes that need to be decarbonised, moved to low carbon heating systems. Each of these homes needs about 15.5 megawatt hours per year of energy. And we worked out that we could get 7 megawatt hours per year from drainage associated with housing developments and around 2.5 megawatt hours per year from sewage systems connected to homes. Future buried transport infrastructure construction could deliver a further 0.3 terawatt hours per year of thermal energy. And when you sum this all together, that's 50 terawatt hours per year in total. Interestingly, the transport infrastructure, like tunnels, metro stations, things like that turned out to be a relatively small component compared to drainage and sewerage systems. And these are much closer to homes and offer a real potential for exploitation in the future. And the potential energy and carbon savings from this strategy could also be huge when compared with existing gas boilers. The next step is to reimagine how our entire cities look in terms of how we heat them. We could have all sorts of energy geostructures, tunnels, metro stations, sewers, all equipped for ground heat transfer and storage and connected to district heating networks where we can connect industry, waste heat from data centres, different sorts of public and commercial buildings, and other sorts of ground energy storage like aquifer thermal energy storage or borehole thermal energy storage, all circulating fluid through a low temperature network. This is a vision of the future we should be trying to achieve. But it's not always possible to get things delivered just by getting the ground engineering right. We need to think about where things sit in a policy environment as well. I've recently been involved in a project looking at the issue of ground heat exchangers that are shared. This is where a number of houses or tower blocks are connected to a shared ground array to extract heat from the ground, as opposed to an individual ground source heat pump system on the left or a district heating system that I've just mentioned. However, currently in the UK at least, there is not a good policy environment to support these kinds of developments. The government's recent strategies for heating and buildings, they focus very much on one end of this system or the other end of this system. And there just isn't anything there to support the development of these mesoscale systems. So we have a lot of work to do, not just getting the geotechnical and ground engineering right, but also communicating what needs to be done to wider audiences and engaging with policy to help shape a better future. Another big challenge of the current years is climate change, of course. This is very relevant for lots of areas of geotechnical engineering. I first started thinking about this when I was still working in consultancy. I've already mentioned how we were thinking about how wetting and drying cycles impacts earthwork performance and how shrinkage and swelling might affect clay embankments. But here are some summaries of other processes that might be relevant. We've got precipitation, which can either infiltrate or evaporate into earth structures. Seasonal variations that can cause slope deformations, maybe serviceability challenges that I've mentioned, but also ultimate limit state issues, actual slope failures caused by raised pore water pressures in winter, all of which can lead to unacceptable performance of geotechnical assets. Whilst I first started thinking about these things as a consulting engineer, and at that time also started feeding into research programs as an industrial partner, since I've gone to become an academic instead, I've later had the opportunity to join and lead research challenges in this area. I'm just going to mention a couple of things that are ongoing at the moment. I'm part of a large program grant called Achilles, where we've been looking at the deterioration of high plasticity clay slopes. Some work of my colleagues in this program is shown here. We've got the results of a centrifuge test by Andy Take with vertical displacement and horizontal displacement for a clay slope, with the black dots being the centrifuge results and the red lines being numerical simulation that's been validated against that centrifuge test. That validated model has then been used to look at what happens in the future if we project forward the behaviour of clay slopes with climate change. And what we're seeing in the bottom chart is the mid-slope deflection of those, the mid-slope deflection of such slopes cast forward many decades, first of all with weather sequences applied from the recent past, and then with a number of future climate scenarios. You can see that depending on the climate scenario, the point at which this line goes vertical or the slope might fail, it depends on the climate change scenario that we've selected. And the amount of rainfall required to trigger the failure depends on that too, with more severe climate change scenarios bringing failure sooner and less severe climate change scenarios bringing about failure later in the future, but requiring smaller triggering events to develop them. This is because what we see due to these stresses and strains and displacements in the slope is a gradual deterioration of the soil properties. We know that soil shear strength against shear strain looks something like this. We have a peak, a critical state, and ultimately a residual strength. Currently, we design most slopes for critical state, which is deemed to be a safe and conservative approach. We tend to pick up a set of strength parameters and a set of pore water pressures and apply them as static in our models with a factor of safety. But as we think about how slope parameters deteriorate with time, actually, if we can use numerical simulation like I've just shown, in order to quantify the changes in displacement or factor of safety with time, we can also use it to tell us where we are on this curve. We can think about it almost as a deterioration curve. And if we do that, and we can categorize the horizontal axis as time, age, or the number of wetting and drying cycles as a slope, we can start to develop design charts like this example here, where we have slope angle against time, a critical state design line, which does not vary with time, and a design life based curve, where we can look and say, if we have a short duration slope, we could get away with a steeper slope angle. And if we have a longer design life, we would need a shallower slope angle. And I think this idea is quite revolutionary because we're used to thinking about design of other elements like steel in this way and sacrificial thicknesses. But it's very often we actually quantify design life for geotechnical slopes. The other part of the equation is about pore water pressures in the future. In the UK, at least, climate change is going to look like this. If we look at the rainfall, it's going to be similar in overall magnitude in the future, but it's going to be more concentrated in the winter, in December and January, and it's going to be less in the summer, in June, July and August. At the same time, the potential evapotranspiration is going to go up, especially in the summer. This means our summers are going to be drier and our winters are going to be wetter. Our winters are going to be wetter and we're going to have an increase in high intensity storm events. So what does this mean for our pore water pressures? On this slide, we can see the results of a series of infiltration analysis into an example clay slope. On the top right, we have winter net infiltration anomaly against a number of different climate models for the 2070s in the future. And on the bottom left, we have the same, but with the summer net infiltration anomaly against these climate models, again in the 2070s compared to the 2030s. What we can see is that in almost all cases, the slopes are going to have greater potential for infiltration in the winter, with an average of about 6.2%. And in the summer, they're all going to have an increased potential for net evapotranspiration in the summer, with an average of 17%, up to an extreme of 45%. So we can see that there will be greater potential for net infiltration in the winter, but they will be exceeded by the potential for evapotranspiration in the summer. This means that actually, for these types of clay slopes at least, we're not expecting more onerous pore water pressures in the future. However, we may still expect more failures because we know that the strength of clays will deteriorate over time. We must also think about different sorts of failures. Away from clay slopes, we may find increases in erosional failures or slope stability, slope instability that is shallow, particularly in granular materials. Finally, I'm going to give a few thoughts towards the future. Increasingly, we need to think about resilience of our infrastructure, including our geotechnical infrastructure. I've talked a little bit about how climate can affect strength and pore water pressure in constructed slopes, but the issues are not limited there. Natural landslides are also susceptible to climate change, and we need to think about their future resilience. Flood defences are going to become increasingly important because we're going to expect higher and more frequent sea and river floods, and our defences need to be resilient to those events. Integral bridges may see increased expansion and contraction with effects on earth pressures behind abutments. Permafrost may fall. Therefore, we really need to develop frameworks for resilience of our infrastructure, use risk assessments carefully using climate change scenarios in the future. The final thing about resilience is it's not just about climate. We need to think about change of use or loading as well. Many sorts of infrastructure are going to be used more, for example, by heavier vehicles or heavier trains in the future. Along my own personal journey, I've mentioned energy geotechnics, particularly related to energy piles or energy from overburied infrastructure. This is already a technical committee and theme of the ISSMGE, and in fact I'm recording this presentation for the conference while I'm at the International Conference for Energy Geotechnics in San Diego. Energy geotechnics is a really interesting area. There are two particular ways we can think about it. We need to do things like bring old skills to new problems. For example, the design of foundations for offshore, onshore wind or other energy structures. But you also need to think about new skills for new problems, particularly how we use coupling of different processes in the ground. Think thermal energy storage, which I've talked about, where we need to couple thermal and mechanical behaviour in the ground, maybe also hydraulic as well. For some topics like carbon capture and storage, we might also need to think about chemical changes that happen in the ground as the ground is used to store different materials, gases, etc. Radioactive waste management is also going to be a challenge for the future. The UK government has just announced it's going to renew its focus on nuclear for the future. So it's a topic that we need to be involved in and contribute to make sure it happens safely. Of course, carbon emissions are becoming more and more important for consideration, particularly in the construction sector, which often gets a bad press in terms of environmental impact. In the UK, the construction sector is well over a third, almost 40% of UK carbon dioxide emissions, of which 75% alone relates to operation of buildings. It's clear, therefore, we need to deal with operation, things like electrification of heat in building, of public and private transport, as well as modal shift in transport to more active transport. We also need to think about reducing carbon in our embodied energy assessments. This is all about materials, using more marginal materials, using materials more effectively, not importing them over large differences. And hey, this is something that geotechnical engineers have been involved in for a long time. We have the skills to deal with many of those challenges. But we also need to think about the framework. Can we price for carbon? How can we share the benefits of reducing carbon? Many governments still want to build construction projects at lowest cost. if we don't consider the cost of carbon, we're not necessarily going to be making the best decisions for the future. I think it's been clear from some of the things I've been saying that the big challenges of the world need tackling by everybody working together, and therefore interdisciplinarity is going to be increasingly important for geotechnical engineers. For the energy challenges I've been working on, like decarbonising this block of flats through the use of ground source heating, we've been working together with mechanical engineers, geologists, water engineers, social scientists, and project finance experts to try and deliver best solutions. Just to take the example of resilience of earthworks and drainage to flooding, we need to work with flood modelers and water engineers as well, cost modelers and statisticians. Everybody needs to work together to make a better world. I'm going to finish with a final thought. I really like this quote from Mahatma Gandhi. If we could change ourselves, the tendencies in the world would also change. And therefore, I think I'd like to finish with this manifesto that if we are working openly, inclusively, collaboratively with others across different disciplines, organisations and countries around the world, then we can really change that world. I hope you agree and you'll join me on that change. Thank you so much.